Hello and welcome back to the Astro Imaging channel. Tonight's session, the title's wrong in the description. I will fix that later, but it is actually simple pixel math operations in PixInsight, or simple pixel math, I believe it is. Presented by David Alt, who is always great for presentations because he really knows what he's talking about, particularly in pixel math. That said, before we do that, I do want to show off our image of the week. This week's image of the week, well, of course, I'm going to pick an eclipse image from last weekend. But as happens every so often, the photographer of this image did not post their name. So whoever it was that submitted, if you will type your name in chat or just send me an email or do whatever, I will definitely let everyone know who took this great image. And I hope you guys all had more luck with the weather than I did. Oop, I don't want to do that. Oops. I hope you all had more luck with the weather than I did. I had about 10 inches of snow on the ground and then a whole bunch of ice falling from the sky. So I did not get to see the eclipse. I just get to see images like this. So thank you. Thank you for submitting, whoever you are. And I also see a lot of great images in chat. So thank you guys as well. We're definitely noticing them. So that said, I am going to take my screen back, but basically I'm just going to hand it right over to David. David, the screen is yours.
All right. Let me start my sharing. All right. Can you see the presentation?
Yes, I see the screen. Yes.
All right. All right. So we're going to talk about simple pixel math. Tolga actually approached me before asking, can we do something that's toned down a little bit from some of the previous presentations I did, and just kind of go through some real kind of basics on how to use pixel math in a couple different scenarios, what it means, what are some of the functions and the nomenclature and stuff like this. So I'll try to break it down into kind of pretty small digestible pieces. And I will just, this is really just talking about pixel math in PixInsight specifically. There is pixel math operations and other tools as well, but I'll just be talking about this here. So there's a couple places where you can use pixel math in PixInsight. The three that come to mind for me are in subframe selector. Both the older subframe selector script and the new subframe selector process in the latest versions of PixInsight allow for math expressions, for image selection and weighting support. They're very specific terms supported through subframe selector related to the data that has been measured that aren't necessarily available through the standard pixel math interface. So there's kind of some things available through some subframe selector and some things available in the pixel math engine, but not necessarily all of them cross on either side. In pixel math, it's a very flexible platform for all sorts of mathematical manipulations of an image. You can use multiple images as inputs along with values and functions to perform any kind of operation. It's not absolutely limitless, but you can do a fair amount with it. The other place you can do this is in JavaScript coding, or if you just chose to, you could do straight C code in PixInsight. They allow for that sort of stuff, right? So it's a lot more flexible than any of the processes, but obviously you have to know JavaScript and be able to code that. We're not really going to cover that here, but I just kind of mention it. Okay, so in subframe selector, most of the math you're going to do is kind of statistical in nature, right? Ultimately, the goal is to limit or weight a set of images so that when stacking later, you can end up with a higher quality result. What qualities you're looking for can alter what your expressions are going to look like, right? So if you're really trying to get maximum resolution, you're not that worried about signal to noise ratio. You have plenty of data, but you're trying to maximize your resolution. You're going to weight really heavily on full width half maximum, right? Whereas if you don't necessarily have a lot of data, you're not really trying to get highest resolution. Say there's only a few stars and you've got a lot of nebulosity or something like that. Resolution is not as important. Then you might weight more towards signal to noise ratio or noise or one of the other estimators in subframe selector for that. So let's take an example. Say I wanted to focus on minimizing full width half maximum. I might do one of the two options that I've shown here. In both, you can see that the highest full width half maximum, that's the blue line, ends up with a weight of 0. That's the dotted gray line. So both of them, the maximum full width half maximum, that's the largest stars, meaning the lowest resolution you have. The weight is smallest for that guy. The first one uses an inversely proportional expression. That means you've got a 1 over full width half maximum in some way. The second one uses a 1 minus function. Both of them were normalizing the full width half maximum. We'll talk about that later. The 1 minus x requires normalization. The inverse function doesn't. But you can kind of see if you look at the bottom one, which is the 1 minus x expression, it looks very linear. So if you kind of draw a line through the average, the mean of each of them, you can kind of see they look basically flipped on end, flipped vertically. Whereas the one above, which is the non-linear, it's a 1 over x function. You can see it looks a little different, right? And that's because it is a nonlinear function. Both can have their uses, but you can kind of see, how these things may look when you do that. Adam, are there any questions coming up so far?
Not yet.
Okay. Okay, so let's break down the expression here. Whenever I call out FWHM in a subframe selector expression, that's going to return the full width half maximum for any given frame that it is looking at, and it's going to loop over each frame as it's doing these calculations. So you're going to have subframe selector up, you're going to select a bunch of images, you're going to measure them, and that will be, for this particular image, what the average full width half maximum was for that image. The new process, subframe selector process, has full width half maximum min and max functions. This will return the minimum and maximum data for the entire set of images that you're looking at. You'll kind of see in the table what that looks like, so it'll make a little more sense then. You'll also see that I've got this kind of expression in here where I'm taking the full width half maximum minus the full width half maximum minimum, and then divide that by the full width half maximum minus the full width half maximum minimum. This is called normalization. Effectively, what I'm doing is taking the range of values that the full width half maximum varies by, and that's the denominator, the bottom component here. I am essentially adjusting it. So I'm subtracting the minimum from each, so they're both set to 0 for whatever the lowest value is, and then dividing it by the range. And what this guarantees is that whatever full width half maximum value I'm measuring will always be in a 0 to 1 range, right? So this is normalizing. And you can kind of see when I step through the table, what that's actually doing here. So let's kind of go through the table a little bit, and we'll kind of walk through. So the table shows incremental steps of adding the expressions around here, right? So the first is just the image index. The second column is the actual full width half maximum average for that image. You can see at the bottom, I have the minimum and maximum of that data set. The minimum being 1.7 and the max being 6.4. And in the third column, you can see this is the normalized full width half maximum. And that maximum 6.4 now has a value of 1, and the minimum 1.7 has a value of 0, and that all of these land in that range. So the next term after that is just kind of adjusting it. In this case, I'm adjusting it into a 1 in 10 range. So you can see now that the maximum is 10 and the minimum is 1. And then the next step is inverting it. So you can see I do an 11 divided by that. So if you look there, you'll see that the maximum is now 11 and the minimum is now 1.1. But that's inversely proportional to the previous one. So now you can see in column, was it 4 versus column 5, the lowest full width half maximum is now the highest value here. And conversely, the highest one in column 4 is the lowest one in column 5. So we've inverted that. And then the last step is just putting it in a 10 to close to 0 range. So you can see that, you know, it's just kind of setting it into a known range out of that data set. All right. So you can get pretty complex with your expressions. So this is just an example where I'm measuring the signal's noise ratio weight, the full width half maximum, and the eccentricity of the image, and using that to create a scoring for my data set. You can see that the weight for the signal to noise ratio is 20. The weight for the full width half maximum score is 50, and eccentricity is kind of low. I've also put an offset on here so that nothing will go below the value of 30, so that whatever I do, I always have something above 30, and whenever I go into my actual stacking algorithm with this weight, something will always be adding some value to the final stack. If you look at the two results out of this, in the one on the left, the blue line is full width half maximum, and the one on the right, the blue line is signal to noise ratio weight. So this is an approximation of the signal to noise ratio in an image. And you can see the dotted line in both cases is the resulted weight here. With the weighting of 50 on the full width half maximum, you can see that whenever there's a really big spike in full width half maximum, there's a really big dip in the weighted output. You can see some other things like, you know, it kind of follows the signal to noise ratio. If you kind of follow along, the graphs are kind of parallel-ish. But you'll see, like on image with 1, 2, 3, 4, image 4 here, you know, you have a dip down because the full width half maximum jumps up. Likewise, you know, this image here, the signal to noise ratio wasn't significantly worse than the other ones around, but the full width half maximum was so large, it gets penalized a lot. So this kind of gives you a way where you can balance things out. You can focus on one thing over another. It's just a general way to kind of tune the types of results that you're trying to get out of subframe selector. All right, so that's it for the subframe selector piece. Do we have any questions, Adam?
Someone's asking right now if we can make the figures and formulas larger. And John, I'm going to post this in the description of the video, but I just posted it in chat. This is a link to the presentation, so you can get in there. I don't think we can actually make the formulas larger on our end.
Yeah.
You'd have to like change the resolution of your monitor and actually make it bigger, which may not work for you depending on what kind of monitor you have. So the link to the presentation is right there in chat.
You can also zoom in on the PowerPoint using the tool, like the tools. If you hover over the lower left-hand corner of the presenter of your screen, then he can make the like zoom in on parts of the PowerPoint if you want to show something.
Yeah.
Yeah.
Yes.
It might be easier for you to go to the presentation though, because that's a big,
Yeah.
long line to have to copy.
Yeah, just if you want to showcase something while you're
Yeah.
talking, that could be a way to do it.
Yeah. So yeah, definitely go take a look at the presentation. Some of these things might be, like the table might be a little hard to read otherwise. I know the live stream is not the highest quality compared to what we record and put out there, but.
And then Ray was asking why subframe selector is taken as an example for Pixelmath. And Tolga just said same type of formula applies. I don't know if you want to elaborate on that.
So the point of this is where can you use math inside PixInsight, right? And you can use it in both these places, right? You can see I'm doing math here of some sort. In this case, it is a kind of statistical in nature to get a desired result. I'm not trying to manipulate a specific image. I'm trying to get a desired result out of it. And when I was talking to Tolga about this, there was a lot of questions about, well, where do these expressions come from? A lot of people are using stuff that I or Mike or others put together in a spreadsheet some time ago for some of the weighting algorithms and stuff like that. But, he said, well, I've been using this for a while, but I don't understand it, right? So that's kind of where this came from.
And I think you mentioned earlier on subframe selector, you're basically doing like statistical analysis, so to speak, whereas in Pixelmath, you might be doing a different, at least for me, I would do blending in Pixelmath. But we'll see where you go with your presentation.
Yeah.
I think, oh, okay, that's an answer. Yeah, Ryan's answering the question.
Yeah.
I'm always jumping around in the questions. All right, go ahead, David.
All right. So now we'll jump over to the Pixelmath process. And I'll just kind of break down all the elements of the GUI first. There's a lot of aspects to what's going on here. This kind of first red colored section, this is where all the expressions you are entering that are going to perform the math operations you're intending to perform will be entered. The green, highlighted green area is where you'll define symbols. We'll talk a little bit more about that. They can also be initialized here, meaning you can set to a constant value if you chose to. This next one, use a single RGBK expression. This can be turned on and off. So for example, if I was working on a color image or a color image with an alpha channel or something like that, I can do all the math with a single expression, or I can do it separately for each color component. So for R, G, B, or alpha. And that toggle just turns off whether I'm doing it with a single line or multiple independent equations per color channel. The button below that, the expression editor, launches the expression editor form. We'll talk about that more in a second. So controls for how Pixelmath runs this section here. You can actually disable generating the output. If you just want to do some process on data and look at what happens in the console, you can do that without actually creating an output image. You can run single-threaded if you choose. I've not done that in a long time. Pretty much always use multi-threaded at this point. And you can tell it to work in a 16-bit working space. The default is 32. But if you really think, I've got a lot of data volume here, say I'm manually making an HDR image or something like that, and I need the additional floating bit working space, then you can do that. The rescale results section simply does that. It rescales the result to whatever you've defined here. You can't do any more than 1 or any lower than 0, so you can't have a negative result or anything over 1. All interpretations of image data in Pixelmath, the image data is always interpreted from 0 to 1, floating point 0 to 1 value. We'll talk a little bit more about that in a second. The next section allows you to swap between applying this process to an active image or creating a new image as a result. And the last section simply allows you to specify how that new image will be created. So you can have a new image that is created that is different from your input images. So for example, you could have 3 monochrome images coming in and be outputting a single color image from that. Okay, so this is the expression editor. So if you're doing really simple stuff, it can all be done in line just on the main GUI. But if you're doing some more complex stuff, then it's probably better to bring up the expression editor. Allows you to do some kind of quick things, like if I want to bring in a specific image and I've got a really long image name on that window, you can just go through and click on the name of it, double click on it, and then it'll pop it in wherever your cursor's at in the expression over here. So it gives some kind of nice things to make things a little bit easier when you're coding up your expressions. The first section is the expression area. You can see it's broken down, the RGBK, green, blue, alpha one, and then a separate one for symbols. So you can click on each of these tabs and enter your expressions there. The next panel down is the information panel. So if you select a function or an image or something like that, it will give you, some sort of information about that. Sometimes it'll be documentation about how the function is called or what it's doing. That can be really useful. And the last one is kind of a checking box. So if you click the parse button on here, it'll check to see whether your expression is valid and give you kind of some results back on that. The images panel just lists all the valid images that can be used in your expression. If you've defined any symbols on the Symbols tab, they'll show up here, so they can be quickly referenced. And the last box is all the functions and operators that can be used inside the Pixelmath engine. All right, so let's go over some basic terms and kind of operations of Pixelmath. Like I said, image data is always represented as 0 to 1. If you've got a 16-bit image stored as FITS data or whatever, EXIF or something like that, and that data is stored as 0 to 65535 in the file, doesn't matter. When you bring it in, it will be represented as 0 to 1. So if your pixel value is 0, it'll show up as 0. If your pixel value is 65535, it'll show up as 1. Same with an 8-bit image. It ranges from 0 to 2555. That'll be compressed into a 0 to 1 range, right? Pixelmath runs in a loop over each pixel in an image. So whenever you're making your expression, just remember that it's being done on every pixel in the output image. We can talk a little bit more about that in a minute. Sometimes you'll see in Pixelmath expressions $T. This is the active image. So in place of saying I've got an image called something 1, right? So instead of typing in something 1 for the image that this process is going to be applied to, I can put in $T. And then if I hit the apply icon, and that's my active image, or I use the new icon new instance icon, and drag it to this image, it will be applied to that image. So once the Pixelmath process is complete, that active image is updated with the result of that Pixelmath process. So if an image has multiple channels, red, green, blue, and/or an alpha channel, this can be indexed by appending a channel number to the image name in square brackets. We'll show a little bit more of this, but let's say I have an image called test image. Test image bracket 0 refers to the red channel of the test image. Bracket 1 is green, bracket 2 is blue, and bracket 3 is the alpha channel. You occasionally see the tilde operator in Pixel inversion. This is a 1- value. So that's directly what it is. It's equivalent to saying 1 minus $T or something like that. This works really well because it is, the data is always compressed to 0 to 1, and then it effectively changes that value to 1 to 0. Right. I use the inline if quite a bit. So this does an inequality expression test, and say this evaluates to true, then the first operation will be the result. If it's not true, then the second operation will be the result. So for an example, if I do this inline if x, this is an x function. This basically reports where in the image Pixelmath is at in x coordinate. So if x is greater than 600, I'm going to return 0. Otherwise, I return the current image data, right? That's this $t again. So you can see as it's iterating over each pixel in the image, once it gets to an x value of greater than 600, it sets that value to 0. Otherwise, it returns the current value. So you can see that it turns everything in the image that's past x equals 600 to 0 in the image. Any questions so far, Adam?
We had one thing pop up, but I think I'm going to save it till the end.
Okay.
For those of you watching chat, you know what I'm talking about. But it's one of those rabbit hole things that we could talk about for half an hour if we don't. So you keep going, and then I'll bring it up once your formal presentation ends.
Okay. Okay, so here's... Oh, sure.
You said if you go back to the last slide,
The
inline if statement.
Yeah.
Right. You said 600, right? But I thought in the first you said the values only go from 1 to 0.
The data value only goes from 0 to 1.
So what's the 600? That's my question.
So that's the coordinate. So this is the coordinate. So this is the x coordinate in the image. So x parentheses is returning where the loop is when it's operating over every pixel in the image, where the x coordinate is in that loop, right?
Right. So that's not a pixel value. That's where it is in the. So you're basically trying to do something to a part of an image.
That's right.
Got it.
Right. So that x parentheses function is a function predefined, right? There's also a capital X parentheses function, which returns the coordinate space in a 0 to 1 range as well. So you can do it in a 0 to 1. And that effectively means that the left edge of the image is 0, the right edge of the image is 1. That can be useful for other reasons too. But in this case, I'm using the lowercase x, which is going to return the coordinate where the process is at in the loop over all pixels. All right. So this is a blending example. So we've talked about SHO before. So I'm just going to show a kind of simple example going through two different versions, right? In both cases, the options are changed from the default. Specifically, I've turned off use a single RGB K expression. That's disabled. So that I can operate on the color channels for the output image separately. You can see I've set the create a new image option on so that it will create a new image as a result. And I do that because I want to create a color image out of monochrome data. And you can see I set the color space to RGB color so that I will get an output color image. Otherwise, all values, the image width and height will be the same as the input image. All right, so on the left, each image is assigned to the RGB output just directly. There's no math involved. S2 is assigned to the R channel. HA is assigned to the green channel. O3 is assigned to the blue channel. And when you run this process, you can click on, if I've got, say, S2 selected, you can click on the Apply button. It will use the S2 image data for populating all the image width and height, color space, all that sort of stuff, sample format. Or you can drag the new instance onto the S2 image. That will work well. So you don't have to have an active image for that. The second one, I'm doing some blending between the different inputs. So in this case, I'm blending half of S2 and half of HA. So you're getting a 50-50% blend between the S2 and HA images for the red channel. And then green gets a 30-70 split between HA and O3, so it's primarily O3 image data. And the blue channel gets nothing but O3. And so you can kind of see the differences here, right? The one on the right gives something a little bit closer to a natural color palette, meaning the stuff that's roughly red is roughly red in the image, the stuff that's roughly blue or green is roughly blue or greenish, versus the SHO palette, right, where your reds are directly mapped to S2 content, your greens are directly mapped to HA content, and your blues are directly mapped to O3. So you can clearly see the oxygen shell, which is really blue around the Crescent Nebula. You can see kind of a greenish yellow mix here because this area is both strong in SA and HA. And then there's a lot of greens and stuff in here because you've got a lot of HA in the image relative to the others. All right, so this is kind of a simple way to blend data. It can be done other ways as well. For example, I could make a new red image by just running this single expression, just sorry, you know, 0.5 times S2 plus 0.5 times HA. It's a 50% blend between the two, and make a new red image. Then I could do the same thing for green and for blue, and then use the RGB combination tool to make an image as well. That would work. This just makes it easy to do in one place.
David, were these particular images, channels permanently stretched and used linear fit?
So I think in this case, nothing was stretched. I've got the STF stretch on the image data.
Okay.
So they were linear fit so that they were roughly in the same data range, but that's it. Otherwise, they were linear data.
Gotcha.
Yeah.
Thank you.
All right. So a little bit more blending with Pixelmath. Blending is pretty straightforward. This is really easy in tools like Photoshop to blend things. What we're going to do here is effectively a normal blend, or also called an alpha blend. You know, but this can be done pretty simple in Pixelmath as well. So in this particular case, what we're trying to do is a 40-60 blend between two images. And effectively, I want to take 60% of my active image and blend it with 40% of what's in this case a noise reduced with some contrast built into an image, right? So you can kind of see the active image on the left, the noise reduced image on the right, and the expression that I'm using here. It's pretty straightforward. I have a symbol called A, which I've predefined as a value of 0.6. And I'm multiplying A times $T, which is the active image, and then adding the inverse function, tilde A. So that's going to be 1 minus A times the noise reduced image. So you can see in this case, that's going to be 40%. Doing it this way, A times some value plus tilde A times another value, guarantees that your two values will never add up to more than 1. It'll always add up to 1. So it's an easy way if you have two values to just do it. And then this is like move slider, you know, on a opacity blend between two layers in Photoshop, for example, right? So this would be like the value was set to 60, for example. So in this case, you know, I'm showing that I'm using the new instance icon. I'm dragging it to the active image. This gets applied, and it uses the NR image data, which is directly referenced, and then gives you the new output image. So another kind of very simple example to show you what is actually happening with the blending, right? So in this case, I'm doing the exact same thing. I have a happy image and a sad image, and I'm taking 25% of the $T image. So you can see I'm applying this to the sad image. and that means 75% is going to come from the happy image. So you can clearly see that the sad face part of the image is very light compared to the happy face part of the image. So that's 25% versus 75%. So just a conceptually easier way to see what's actually happening in this blend. All right, any other questions?
No other questions yet.
Okay. So there's some other types of blends that we commonly use. This is a kind of simple one, just using the max function or the maximum. In this case, it's going to take the max of these particular images. Now remember, Pixelmath is running in a loop. So what this is really doing is saying for pixel at coordinate 0, 0, take the maximum of each of these images. So it'll take the star mask 1, 0, 0 pixel, the star mask 2, 0, 0 pixel, the star mask 3, 0, 0 pixel, and compare them and take the maximum of that value, and then that gets returned for your final image for coordinate 0, 0 in the image. So it's this process is running over a big loop, an XY loop over the whole data. And what you can clearly see here is on the left, you've got a star mask for a bunch of the smaller stars. A second star mask that's emphasizing the larger stars and growing them a bit. And a third star mask that's growing them a lot more and only capturing the brightest stars. So then when I blend them together, I get the result here where I've got pretty much everything represented, with more brightnesses that will work for a mask that I'm trying to do. This is a pretty common way for combining star masks. Sometimes you might use addition and things like this, but this tends to work pretty well for most cases. All right, another kind of simple one, blending with alpha channels. So in this case, I've got a beard image that has alpha, and you can see PixInsight represents alpha, a alpha value of 0, as a checkerboard pattern, meaning that there's no content behind the image, and 1 will just represent the image data. You can see in the expression that I'm referencing the bracket 3 index, which is the alpha channel index. Remember, 0 is red, 1 is green, 2 is blue, and 3 is the alpha channel. And effectively what I'm doing is this image will be applied to the face of the female drawing face on the left versus the beard image on the right. And I'm checking to see if the beard image has a value greater than 0. If it does, then I'm going to do this blend. Otherwise, I'm just going to return the image of the face. The blend here is using the alpha channel. So it's doing that same kind of normal blend that we saw before, except instead of having a constant value, I'm using alpha value from the image. So the alpha value times the beard image value, tilde the alpha value times the face image value. So it's doing a blend between those using the alpha value. And then when this is applied, you can see it blends in. The areas that are clear end up as the face image, and the areas that have more density of alpha value show up clear through here. So we applied the beard to the drawing of the face. All right, so that's it for the main part of the presentation.
Yeah, question on that alpha value. So an alpha channel can be a full color image.
That's right.
Huh. And
they can be grayscale images too. You can have 2 channels, right? 1 alpha, 1 grayscale. But you can have a red, green, blue alpha image as well.
Huh. And does it not treat the background value as 0? In other words, like a maximum wouldn't work on that?
I'm not sure what you're asking, Adam.
So the non-beard board pattern in the back? Does Pixelmath not see that as 0? If you were to do a maximum of the face and the beard, would it not work because you're just using the alpha channel?
So in particular, I'm trying to get it, because there are areas in the beard image that are non-zero alpha channels, they're somewhere in between. I'm trying to get it to blend with that, right? If you do a max function, it's going to be either or, right? In this case, yeah, it's going to take the darker of the two, right? Or the brighter of the two with a max function.
Gotcha. So you're getting a blend instead of just
right.
I gotcha.
But if you actually take this, and I think I have the beard image in here, right? So let's take a look at it. So I'll bring up the beard image, and I'll just do something really quick where I'm going to take the beard image, and I'm going to take whatever that image value is, but I'm going to set the alpha channel to 1 across every pixel in the image. And you'll see that there's other content in here that's effectively been turned to 0 by using the alpha channel, right? So you can't guarantee that a max function will work in that case, right?
Gotcha.
Right.
David, on your website, do you have the list of Pixelmath expressions that are equivalent to the blend modes in Photoshop?
I don't know that I have them on there, but I do actually have them in a set. So I actually have all of them in here. Multiply, screen, overlay, dark and lighten, addition, subtraction, division, soft light 2, hard light, things like that. I actually posted them when I did the presentation, which was the advanced Pixelmath. I posted a set of PixInsight icons that people could use. I can do the same thing again for this presentation. I was actually going to post the whole project that I have here that shows some of the various blends and stuff like that, but my internet bandwidth is not great anymore since I kind of moved out into the country, so that would have been kind of tricky to do. But I can take just the skeleton of it with all of the processes on here, like these guys. And so y'all can.
We just got it.
Go ahead.
Yep.
Okay, so I'll do that. I'll send that to you, Adam, so you can post it.
We actually got the old presentation with the I think the equivalents in chat. So
okay, yeah.
Go with what you're doing. I think we got it covered.
Okay. All right. So there's a couple other things I wanted to kind of show. So let me do this one real quick. So this is just the blends. So I'll kind of show those real quick. So these are just the SHO blends. This is a direct SHO. That was just clear these out. S2 HA03. I'll close this one real quick and just run it on the images. I'll select one of these before I hit apply. So you can see I just get this SHO image as a result. Similarly, the base one is actually this guy. You can see there's different numbers here between this and the alternate. It's just slightly different blends. My alternate form has a little bit more kind of orangey colors to it rather than straight reds. I tend to like that in my images. That's kind of personal preference, right? I also have in here, so we have the beard one. That one's pretty straightforward. I also have one, let's say, I've kind of run into this before where I've had problems combining a mosaic with gradient merge mosaic. I keep running into issues where, even notching something, the stars out sometimes isn't working very well. And so sometimes I'll resort to, I'm just going to blend these panels together manually, right? So I've got, a set of images that are, all my panels, right? Everything's been registered. Everything has been linear fit between all the frames. So everything matches up. And really what I want to do is just get them put together. So a lot of the times what I'll do, and this may be a little bit hard to see. I'll just square these things off. So you can see that all I'm going to do is just cut the edges so that everything is kind of squared off. Zoom over. You can see I'm just cutting the edges off so that I'm guaranteeing that the box I'm looking at is square. And this will make it easier for blending between two panels, right? So for example, you know, this one is going to trim, what's it, panel 4. So you can see I'm doing the similar to what I did before. If X, the X coordinate, which you can kind of see, well, you probably won't see on this screen here, but at the bottom it's showing wherever my cursor's at, X is equal to, say, 1350. If I move to 1363, where this is saying, then it's right at the edge of where this is completely illuminated in this box. Similarly, if Y is greater than 1009, which is about the bottom of this, if anything's past that, then I set it to 0. And that just kind of cuts off the edges and squares it up, right? And then when I go to blend, I'm doing effectively an alpha blend, but I have to compare to make sure that I'm blending between coordinates. So in this case, I'm actually setting coordinates, 937 and 1009 in Y values. I'm blending between panel 1 and panel 4. So what I've done is I've looked to see, well, what's the lowest coordinate of this and the highest coordinate of this? And I want to blend in only in that region. And I effectively want to blend based off of the coordinate that I'm looking across. So it gets a little complicated, but this gives you a way to blend across those panels, right? So if I do this, it's going to create a new image. You can see it's blended across there. It's pretty hard to see the seam where that blend occurred. But it should be somewhere in the 937 to 1009 range, which is roughly about in here. You can see there's a little, well, it's going to be hard to see on the video, but there's a little bit of blending that's somewhat visible on that seam, but otherwise, you know, from a wide scale, it's not that visible. And that's mostly because signal to noise ratio between the two panels was not as clean as it could have been. So you can do that over and over, blend between these two, then blend between these two, making new panels, blend between these two, and then I have 3 new panels, and I can blend between the left 2 and the right 2, right? So these are blends for each of those, right? And then I blend between this one and this one. And that gives me this one, and then finally generate, you know, the whole combined stack. So sometimes if you run into problems, you can do it like this as well. One other thing that I've put in here, long before there was a hyperbolic arcsine stretch function, I've been doing stretches like this before. You can see I'm using the arcsine H function, which is the hyperbolic arcsine. You can do it with Pixelmath. It's pretty much equivalent, although the process is a lot quicker and easier for doing these things, and allows you to set clipping points and stuff like that, which this doesn't do very well. But you can see, you know, for quick stretches, you can do things like this too. Sometimes you may want a log stretch over something else, and it's a quick and easy way to do it with Pixelmath. All right, so that's pretty much it for the presentation. So why don't we go to your tricky question, Adam, or if there's any others that popped up, or anyone wants to see anything in particular demonstrated.
Okay, so when you were going through your image analysis, Adam Block posted this, and he said that he finds it interesting that most images give so much weight to full width half max, For him, signal-to-noise ratio seems more important, particularly for deep sky. And his thinking being, if you can't see the signal, the resolution doesn't really matter. I know your formula kind of takes both of those into account, or can, right? So what's your comment on that?
So my comment is, the point of that is to tune things, right? So let's say that I know that I've got a huge amount of signal, more than I would really need, which is probably pretty rare for most people. But let's say that I know that, right? And that I'm not worried about my signal-to-noise ratio coming up good. But I am worried about getting super fine details in the middle of this galaxy, right? In that case, I'm going to tune for full width half maximum, right? But it's a tuning statement. It doesn't have to be one way or the other. It can be favoring one over the other a little bit, right? And that's all those weightings give you, right? I completely agree with Adam that in a lot of cases, you know, the signal-to-noise ratio is what we're going for. We're all pushing against the clock in terms of getting the most signal-to-noise ratio in the shortest amount of time, right? But if your goal is, I want to achieve maximum resolution, then that's how you would weight it. You would weight it for full width half maximum. Right?
Mm-hmm.
What I have used this formula in two different ways is that, let's say we're doing the Crescent Nebula, where there's something bright and we're trying to get a lot of details out of the crescent, but the rest of the image is nebulous, means that it's not sharp. So what you could do is that you could create two masters, one by weighing by signal-to-noise ratio, one by weighing it heavily by FWHM, and then blend those together and use the best parts of both worlds.
You can definitely do that. You know, it certainly does work. Tolga, I'll ask this. When you do that, are you selectively blending between things, or are you doing some sort of math blend between, just like a straight? How are you picking and choosing?
Right, that blending part, I actually do. I don't know how to do that in PixInsight. I do that blending in Photoshop with masks. Like I'll put the two L's on top of each other, and I'll paint over the shot. You know, let's say, going back to the example of the Crescent Nebula. So I have two Crescent Nebula L images. One was stacked weighed FWHM, and one was stacked weighed by signal-to-noise ratio. And then I'll put those on top of each other, and then I don't know how to do that in PixInsight.
Yeah, no, you can blend with masks and stuff too. In fact, a lot of the time, whenever I'm doing blending, so let's say I have two images, I just want to blend between the two. I'll clear this one out. And I want to do a 50% blend between my noise reduced, contrast enhanced image and my current image. I may take this off and turn it into a mask, right? So I'll apply it as a mask to this image, right? So you can see I'm going to invert the mask so that it's mostly applying to the background, that the galaxies and stars are mostly protected. So when I blend, I'm mostly affecting the background. And a lot of times I'll do this in stages, right? I'll do a blend, you know, that affects the background more, and then I may do another blend after that that's kind of general purpose, but I'll give a little more weight to the original image, so not blending as much as I would have otherwise. You can do blends with Pixelmath as well. The mask will protect just like it does any other process.
I'm muted. Nope, you can hear me. Yeah, Adam Block saying in Pixelmath, the way to do it would be to blend with the mask based on brightness, which seems to be the way you were doing it there. Same kind of thing that's done with deconvolution. For deconvolution, I use a mask from the same image and just try and focus it on the brighter spots. John is asking, can Pixelmath be used to remove fine background speckle?
find background speckle. To some extent, yes. You know,
I'm gonna cheat to do it, but I don't know if I feel comfortable. I
you
mean,
know,
you can
there,
arbitrary lower value.
yeah, there are lots of ways you can do things like this, right? You know, I think I have you know, some kind of fake noise reduction algorithms, right? And again, you'd want to do this with a mask of some sort, because you only want it to operate in the background, but we'll kind of do a simple one here. All right, so you can kind of see it somewhat blurs the background, but what it's doing is, let me see if I can expand this enough. Probably not. I'll go to the expression editor. And you can see the expression in this one is quite complex, right? Effectively, what it's doing is taking a group of pixels in a box, right? In this case, it's a 3x3 box, and is doing a bi-weight mid-variance expression to approximate, to get a kind of a standard deviation result, and then is clamping it based off of that standard deviation result, right? So it kind of clamps in the background value based on this, you know, kind of tile as it's rotating through. So you can do things like that, right? That kind of reduces a little bit of speckle, but it also kind of blurs the background a little bit. Honestly, for kind of things like that, I've found that it's just generally easier to do some sort of noise reduction. One of the linear was, I can't remember all the names now. Things like the multi-scale linear transform, multi-scale median transform, TGV denoise, things like that. I generally find those better for doing that sort of thing.
Yep, and you're getting some agreement in chat, and for me. Any other questions in the room on anything we've gone over, anything related? I'm still surprised PixInsight hasn't, I know they're philosophically opposed to it, but I'm still surprised somebody hasn't developed a kind of simple layer tool that does just the basic processes like maximum, minimum. That said, you kind of have to learn PixInsight the PixInsight way and not really try and make PixInsight conform to the Photoshop way. I don't think
it's a tricky thing to answer, right? You know, layers are extremely powerful, right? And you know, you have to ask, do you really need them in PixInsight, right? A lot of us have Photoshop and PixInsight, and it's use the appropriate tool for what you're trying to do, right? So, you know, I tend to, if I need something where I'm doing really complex blending like that, then I'm going to go over and do it in Photoshop, right? What I just showed there was kind of a simple, if you know, I occasionally want to do some really custom highlighting of things, and I went over this in the advanced Pixelmath presentation I did. Well, it's been a couple of years ago now, I think, right? But yeah, you can do kind of interesting things like this where you're drawing shapes on your image and stuff like that. It can get pretty complex, but it can be pretty useful as well for highlighting, you know, indicating a star or having custom ellipsoids and things like that around specific objects.
Very cool. Thank you, David, for presenting. We are going to be off next weekend for the Super Bowl and my wife's 40th birthday. But the week after that, we'll be back on. I'll get something posted sometime between now and then. We'll definitely be doing something. Otherwise, you've got about a minute to ask your questions, or else we'll be ending the session for tonight. Again, thank you, David, though, for another great presentation. And Thank you all for your questions. I don't see anything new coming in, so like I said, see you guys in 2 weeks. Session will be posted sometime between now and then.
I just want to mention. I know I keep saying it, and I'm going to say it every week until April. NEAF and NEAC is coming up. You know, if everybody's interested, go sign up.
Definitely. Don't want to miss that one. And we'll keep repeating it as well. Thank you guys. See you in a couple weeks.